The main scope of this webinar is to share with you how combining generative design and 3D printing of composites could be a challenging and very exciting approach for developing grippers for robots. Okay, so the presentation has three sections. First of all, we are going to try to put in context the additive manufacturing with the main aspects and very closely related to the need for advanced generative design methods or tools. And in the second section, we are going to explain the main features or most interesting or challenging or more promising aspects of the generative design, very, let's say, general concepts, but I think that are the pillars for developing good 3D printed robot grippers, okay? And at the third section, we are going to show a case study that we have developed, and we are going to briefly show the results in order to have some specific examples how can it be done for developing this kind of grippers, okay? So starting from the context for additive manufacturing, we are going to very briefly make some comments about AM technologies, to remark some aspects of that it's additive manufacturing. It's a direct or digital manufacturing technology. And finally, and even if it looks that it's a technical speech, we are going to talk about economics, because it's very important to analyze the main aspects of the additive manufacturing economics in order to justify the use of these advanced generative design approaches. Okay, so what to tell about additive manufacturing? Okay, but it's one of the key enabled technologies of the fourth industrial revolution, as is marked by everyone, with autonomous robots and horizontal and vertical system integration, the Internet of Things, cybersecurity, and maybe the only manufacturing technology that appears as a key enabled technology is the additive manufacturing. And it's really disruptive, because if we analyze in the pictures on the right, we can see the main families of manufacturing technologies, and the most, let's say, traditional one are formative with casting, injection molding, and so on, and also subtractive. And additive manufacturing could be said that it's a low maturity new technology. So right now, the big question is how do we benefit from additive manufacturing, even if it's not at its highest maturity point? How can we manage, or how can we get a lot of advantages about with these technologies? Okay, so I'm not going to explain all the technologies. In fact, I'm going to not explain no one. But what is true is that the map or the options, technological options for additive manufacturing in the main six, even if there is a seventh one, but the seventh technologies is broader, is increasing. Also regarding to the materials and the capital costings, the compatibility with materials, the dissipation rate is increasing more and more. The part volume is also increasing because the 3D printer are bigger and bigger and so on. But rather to focus on the technology itself, we are going to explain which are the main differences or the main challenges or opportunities to make something different with additive manufacturing. So, from our point of view, maybe the main difference, and which opens new opportunities, is the fact that additive manufacturing can be considered as real direct digital manufacturing technology. And there can be a lot of aspects to remark, but for us, which is extremely important, is that it's a technology that really doesn't need any mold or tools. So it's tool-free or without tools, molds, jigs, and so on. So these main characteristics give several advantages because additive manufacturing is a real flexible manufacturing technology, because then the setup and changeover time are negligible. We can have a sequence of manufacturing starting with a round shape and change to a prismatic one, an hexagonal one, and it doesn't matter which is the geometry and shape of the parts that we want to produce. That we don't need any kind of setup or changeovers. So it opens also this flexibility opens the opportunity to manufacture on-demand parts, okay, with the elimination of inventories and so on. And this is a key aspect. The second one, and it's in the lower part, is that we have a bigger design freedom, because we can the increased complexity of the parts that can be built is higher. So we can get lighter designs, and we can have high functional integration design and so on. And maybe one of the most significant examples, because it's really a critical and high added value product, are the LEAP engine fuel nozzle, where we change, or with the traditional technologies, there were 20 parts that must be assembled and so on, and right now it's just manufactured in one part. So it means that the weight reduction is 20% lighter, and the cost is also more or less than 30% lower, because there are less assembling operations, all quality, all measures, and so on. So it's cheaper. And as important as the cost is this last aspect, that it has been shown that it's 5 times more durable. So it means that the engine maintenance operations are lower, and the costs are lower, and so on. So this can be some of the most important consequences of having this design freedom for the components. And another aspect regarding the shape itself is that, as it's a digital product, we can modify and improve the design from the last part to the next one. There is not mold. We are not depending on modifying the mold and nothing like that. It's just to modify the CAD file, and you can print the new version, the new improved version. So all these are real direct consequences or advantages of being a direct digital manufacturing part. Okay, but this could be considered real technical advantages, but the additive manufacturing influences are not limited to the shape itself. The business model can be also different, because, for example, the fact that we can push, or we can shift for the current manufacturing strategy to distributed manufacturing. It means that we can build the part close to the end user. If we are here at Mondragon and we design our grips here, we can send it to let's say to the United States, or to Switzerland, or to Czech Republic, or it doesn't matter where, and we can print just close of you. So it means that the supply chain is extremely simplified, reducing cost and lead times and so on. We are transporting electronic files instead of physical products, so the environmental impact could be also lower. And even if this is the third one, is that we don't need to invest in machines. We can use the machines that are all around the world in hubs, or some companies that are offering these printing services to us. So you don't need really to invest in manufacturing machines to be able to manufacture your products. Okay, and taking into consideration all these advantages, one of the most important aspects is that customization is possible with additive manufacturing. With this flexibility, with this design freedom, we can customize the products, and we can go from the economy of scale of the traditional manufacturing technologies to the economic of one. So we can go to markets of one product are viable, are possible. It could be really beneficial to develop just one product with these technologies. And in fact, very often, if the product is customized, we can also get a premium price, and the end user could pay a little more, and it could be more, well, better for us. Okay. So these are more or less the main advantages or the context of additive manufacturing. But there are also a last aspect that I would like to share with you, and is the economics. Because when we analyze the economics of manufacturing traditional technologies, with additive manufacturing, there is a small modification that, whereas, as you know, costs are usually divided in fixed cost and variable cost. Okay, and fixed costs are the engineering, design, the marketing campaigns, and so on and so on. And variable costs are the production, the number of units, the materials, the energy, and so on. But which is the main difference between traditional manufacturing technologies and additive manufacturing is that whereas in traditional manufacturing, as we are it's a mass production, the fixed cost is lower and lower with increasing batch size, because it's divided by the number of products that we are building. Okay, and the variable cost, this is regarding the production volume, but if we take into consideration the complexity, the more the complex is the part, the higher is the cost, because it means that the production time is higher, the rejection rates are higher, the quality controls are more complex, and so on. But what happens with additive manufacturing? With additive manufacturing, the optimal, let's say, the opportunities are for small batches and also for high complexity geometries. It means that the design effort is very high, and it must be considered, if we are talking about 1, 2, 3, 10 parts, the design effort is not anymore a fixed cost, but it should be considered as variable cost. Because every part we are designing or producing, it means that we are investing or we are spending some time in engineering and so on. That's why the main challenge is to minimize the design cost of this customized, and let's say even a market of one product, or let's say 10 products per design or something like that, and is to reduce these design efforts in order to be competitive in cost terms. Okay. Well, so which is the main conclusion of the context, taking into consideration the shape, the business model, and the cost. So in order to be successful in mass customization, is enabled by generative design methods, which allow autonomous design according to algorithmic expert systems that emulates manual design methods, but with such efficiency that their contribution to variable cost is effectively nil. So it's to reduce these engineering hours and manpower working on design and engineering. It should be minimized in order to be competitive. So I hope that it will be more or less clear, but we are skip to the second part, and is to describe briefly the main steps or the main technologies or the main milestones of generative design. And first of all, I would like to make a small reflection about evolutionary versus revolutionary designs, and also about which are the digital design steps for additive manufacturing. Well, when we are designing a new product, there are often previously commercialized products, similar products, and so on, that could be used as inspiration, okay? And it's what we call evolutionary design, okay? But sometimes, even if there are precedent designs, the load case answer complex that previous designs are not useful for us. So when we are, and if we are talking about customized grippers for robots and so on, we are talking about something new, something that there is not trivial to develop, and that's something that has no precedent design. So this is the revolutionary scenario for design. So as we talk about just a couple of minutes, it needs a systematic structural optimization system. It means that it should be independent for the designers into intuition or knowledge, and this kind of methods or algorithms is the topology optimization methods. So we are one of the most important, from our point of view, let's say automatic design tools in the generative design approach are the topology optimization methods. Well, and which are the main steps or main milestones when we are designing for additive manufacturing? So it's also a digital process, and some aspects are similar to the conventional design steps. Of course, the first step is the problem definition, where we need to make a clear and unambiguous definition of the outcomes and objectives that to be achieved, okay? And we also have to define the design constraints in a formally way. So it should, and this is the same for conventional design and design for additive manufacturing. But the second step, or the second milestone, is the embodiment design. That it means that very often it's a very idealized representation of the design problem. So we have not a complete understanding of the limits, and the solution itself is not well developed, but it's more or less let's say, a sketch or an proposal, an initial proposal of how the material should be. In this step, we use topology optimization, and as you can see here, we start from a design space with the load cases and the constraints and the parts that must be keep unvariable for assembling and so on. And at the end of this process, we obtain something like that. That is not really the final part, but it's a proposal of the material distribution. Okay, so it's an optimized topology rather than the part itself. But it serves as inspiration for the next step. That the next step is the detailed design. So right now, yes, we have to make the parameters design, defining correctly the specific local geometries, the radius, the thicknesses, and so on. And we have also to check by stress analysis, by finite element method or something like that, that structurally our part is in its integrity it will be fulfill all the mechanical aspects we are looking for. Okay. And what is true is that at this stage, the modeling analyses are more sophisticated and less idealized. They are close from the final part. And it should be, the evolution should be, this is the initial space design, this is the optimized topology, and this is the parameterized design with this virtual validation but finite element analysis. And once we have this initial proposal, it comes the last step, that is manufacturing. But in this step, it's extremely important to make the design for additive manufacturing a reflection and try to apply some rules, because there are a lot of aspects that can change even the original design. For example, the build orientation. Depending, for example, in this gray U-like part, the gray itself is the part, but the red region here are the supports. So depending on the orientation, if it's up or it's down, the amount of support that we need is different. And it means that the printing time is different, and it means that the cost in materials is also different, and so on. But also, and you can see here how the same part that is shown as the case study for this generic explanation. If you see here, these rivets, so these are not necessary, are not defined here in the detailed design, but are just put in order to reduce the amount of supports that in this figure is in blue. Okay, but it also must be taken into consideration that as be a layer by layer manufacturing technology, we are introducing very often an anisotropic behavior of the material, and the layers themselves are with points. So it's not only when you are analyzing the building orientation, you are not only considering the amount and the position of the supports, the structures, but you are also to keep in mind, you have to also keep in mind the mechanical properties you are going to get in your material, okay? But there are some other aspects, as for example, when we draw the CAD in the detailed design, we are drawing the envelope, we are drawing the external surfaces, but it doesn't mean that it should be completely massive design. It could be we can manufacture with an infill that will condition or will modify the mass of the part and the printing time and so on. And also in this step, when we are trying to even modify the design to be easier to be manufactured, we have to also take into consideration the tool part and so on. But okay, with these two slides, I would like to show you that the design steps are clearly defined, and there are different milestones. We don't have the last completely defined design till we analyze the process itself. And it must be a quite concurrent engineering, and the designer should have a minimum knowledge about the processing and so on. They are not separated or isolated knowledge areas of design and manufacturing, and we need really this convergence of knowledges. Okay. Well, and right now we are going to show you how we did apply this approach to a specific case that is was design and validate a new concept of grasping gripper for dismantling fridge gaskets. Right now at the company, they are handmade, so it's not automatized, and there are different ergonomic, health and time and risk problems that could be solved by using an robot. Okay, and okay, the challenge was that okay, there were, you can see here the reference grippers that were in aluminum and so on, and it was to see what happens if we try to change them by an additive manufacturer 3D printed grippers. Okay. So this is more or less the process. We have the fridges to be dismantled, and we want to extract this gasket. Okay, you have here the reference. We take just one kind of gasket, but it doesn't matter because it could be useful for any kind of gaskets for fridges. We modified the concept itself, because in the original part the two fingers were moving, but we decided to keep one just fixed and to move just one of them. And we also in this first stage we defined the available design space, the different loads that must be applied, the attachment points, and so on and so on. So it should be the first step. In the second task, which was the embodiment and the tile design stage, okay, we use topology optimization software. In this case, was Inspire, and the software show us this proposal that it's in Garnet. Okay, but as I told you before in the generic explanation, this is not really a feasible part in order to introduce fibers and so on. So in black, you can see here the parametricized geometry using different tools for as polyneuros structures and so on. And finally, before start analyzing the manufacturing aspects of the part, we have to check that the stress level is low enough to guarantee the structural integrity of the part. And here you can see the evolution of the mobile finger and also the fixed finger. Okay. Well, once apparently the process, the materials were, or the design was validated, we start analyzing the manufacturing of the part. We use a Mark II 3D printer from Markforged, and at the earliest stage, we use an onyx filament that was a microcarbon reinforced polyamide. Okay, the resolution, even I'm not sure that the surface finish was really important, but we use a very thin layer, 2.5, sorry, 2.2 or 0.2 millimeters, sorry, and printing both fingers last 9 hours. Okay, the final weight of the fingers was 28 grams for the fixed and 20 for the mobile, and we use only around 9 grams of support. The original one, the aluminum fingers weight was approximately 100 grams or something like that. I'm not sure right now, but it's around 100 grams. So we reduce, or I don't know. Yes. Well, okay. The details are okay. We are going to talk a bit about that. So, and last, we make the validation of the grippers. Here you can see 2 scenarios. In the first video, you can see the extraction with the reference gaskets, not in the real one, because in order to have better accessibility to the gasket and so on. But in the second one, on the right side, you can see how the gaskets were able to extract. The gripper was able to extract the gaskets. Okay. Okay, if you want additional information or so on, the results are well explained in these communications. Okay, so you can get it in freely. Okay. And what about future lines? Right now we are working because the first prototype was with discontinuous carbon fiber, and right now we are changing to a continuous carbon fiber. So here I put the strength versus density material chart. In blue, you can see the materials is polyamide. Okay, in all cases are polyamide composites, but in blue are the materials for additive manufacturing, and in green is the traditional additive manufacturing. And this one in the lower left part here are polyamide with short carbon fibers. And if we changing or introducing or reinforcing the composites with continuous one, there are a big increase in strength, let's say more than even a factor of 10. Okay. But what is true is that traditional manufacturing as injection molding and so on can be stronger than from the material point of view, not material plus geometry, but the properties of the traditional material are still better than those of additive manufacturing. It's changing because we are improving machines, we are improving materials, we are improving processing parameters and so on, but there is still a big gap between the additive manufacturing solutions or materials and the injection ones. But we are trying, the first prototype was built with this material, and right now we're trying to do with continuous carbon fiber. And here you can see the difference between the onyx or short carbon fiber reinforced polymer solution, and this is in the right, the continuous fiber reinforced solution for the fixed and for the mobile grips. Okay. We are also working on developing a safety cover for the grippers, and we are also trying to, or right now we are trying to introduce sensitive and multifunctionality to the grippers with a camera and also a sensor integration to identify if in the gaskets there are magnetic materials or so on. So, which is really the design freedom that gives us the additive manufacturing technology can make easier to integrate this kind of sensing and monitoring technologies. So, at the beginning, I just asked, how do we benefit from additive manufacturing? And from our point of view, additive manufacturing can be well adapted to robot grippers, as these grippers are geometrically complex that require high customization level, okay? And they are susceptible to be manufactured on demand as spare parts also at place in the factory. And generative design is a promising methodology to reduce the design effort, which must be considered a variable cost for small size batches, but commercial topology optimization doesn't model the anisotropic behavior of continuous fiber reinforced plastics. This is a lack right now. It's a weak point. And also the automatization of the parametric design, considering design for additive manufacturing rules, is low and is still too dependent of the designer itself. So it's not really an autonomous operation that can be made right now. And I hope that's all. Thank you for attending, and we can now discuss the results, your questions, or whatever it is.